Lesson 6-4, Work and Conservation of Energy. We can write work done by an external force as our change in kinetic energy plus our change in potential energy. Why? Because work is a force times the distance, right? And so if I'm moving something, maybe it's changing the position. Maybe I'm moving it up. Or maybe my work, as we're doing a force, a net force provides an acceleration. So maybe I'm changing the kinetic energy. So work equals a change in kinetic energy plus a change in potential energy. You can rewrite it like that. Since each change in is final minus initial, if I add the initials to the other side. Or in other words, our initial energy plus the net work equals our final energy. So that brings us to our law of conservation of energy. The total energy is constant in any process. It may change form, may be transferred from one system to another, but the total remains the same. So remember, so it's energy initial plus our net work equals our energy final. That work would be the energy going into or out of the system. Energy is transformed from one form to another. It's like a box sliding down an incline. The potential energy is transferred into kinetic energy. But as it's sliding, some of that kinetic energy is transformed to heat and to sound. In a car engine, there's chemical energy in the gas. That's changed to kinetic energy to get things moving and heat. A rocket starts on the ground. At rest. And goes up to a height up here. So the final speed is 500 meters per second. The final height is 5,000 meters. So our initial height, let's say, is 0, and our initial velocity is 0, because it starts at rest. Find the work done by the rocket engine. All right, so our initial energy plus the net work equals our final energy. Our initial energy, well, it's on the ground at rest, so it doesn't have any. So our net work is going to be, at the end we have potential energy and kinetic energy. So our mass, it says, is 200 kilograms. G is 9.8 meters per second squared. And our final height is 5,000 meters. At that height, it's also going 500 meters per second. So add that all together, we get 3.48 times 10 to the 7 joules. So what's that, 35 million joules? It's quite a bit of energy. So that's a positive work. Positive work means energy is added to the system. The engine gave energy to the rocket. If the net work is negative, that means energy is taken out of the system. A 1,500 kilogram car's brakes failed and it coasts down a hill from rest. Hill is 10 meters high and the car has a speed of 12 meters per second at the bottom of the hill. How much work did friction do on the car? Well, at the top of the hill, we have a height of 10 meters. And we're starting from rest. So our initial velocity is 0. At the bottom of the hill, our height is 0. And our final velocity is 12 meters per second. And we're looking for work from friction. So our initial energy plus our net work equals our final energy. Our initial energy, we have potential energy. Final energy, all that potential energy is changed to kinetic energy. G is 9.8. Height is 10 meters. M is 1,500 kilograms. And final velocity is 12 meters per second. Okay. So this side I have 147,000 joules. The other side, I've got 108,000 joules. So subtract that, and we get negative 39,000 joules. So this work is negative, which means energy was taken out of the system. Friction always takes energy out of the system. And it did try to slow the car down some. Captain Proton's rocket pack provides 800,000 joules of work to propel him from resting on a ship, which is near the Earth, to 50 meters above it. Captain Proton's mass is 90 kilograms. What is his final velocity? So he starts down here on his ship and ends up here. At the bottom, let's say his height is 0, and he's starting resting, so initial velocity is 0. At the top, he is 50 meters above, and we are looking for his final velocity up there. So our initial energy plus the net work, that would be his rocket providing work, equals final energy. Initially, he has no energy because he's at the bottom and he's not moving. The rocket engine provides 800,000 joules of work. So our net work is 800,000. And our final energy is both the potential and kinetic energies. Mass is 90 kilograms. G is 9.8. Height is 50 meters. Mass is 90 kilograms. So 90 times 9.8 times 50. That's his potential energy. So that 800,000 minus that potential energy is 755,900 joules. That became kinetic energy. Looks like I need to divide by the 45. I get 16797.8. But that equals VF squared, so square root that. And we get approximately 130 meters per second. So he's really moving now. So the rocket pack provided positive work, which means it put energy into the system, So it's able to go from rest to having significant kinetic energy.